Hi everyone, in this video I'm going to introduce using nonlinear equations. So these equations will not be able to be expressed in the general form that implies linearity. If you recall from the previous video in this series on linear equations, the general form of a straight line equation is y is equal to mx plus b. So if you see something in an equation that does not fit this general form, this points to a nonlinear relationship between our variables. Now, the diagrams of these sorts of equations are very often curved like this, or you can think of many other shapes that you might see. Nonlinear diagrams are very useful in being able to describe many different sorts of dynamics that we might see between variables that are of interest to us. And there are many sorts of equations that you might see that fall under this banner of nonlinear. For instance, y is equal to x squared. For instance, this is nonlinear. X is being raised to a power of 2. Another example is if we had a log, so y is equal to the log of x, that will give us a nonlinear relationship. And of course, we can use any variable we want. So we might think of, let's say, a total cost function that relates total cost to quantity, where total cost is equal to 2 times q to the power of a half plus 4. This is nonlinear on account of quantity here being raised to the power of a half. As another example, if we had something like e is equal to 1 over I, this is nonlinear because I, that independent variable, is on the denominator. And so for all of these equations and many more that you'll see, they cannot be expressed in that canonical kind of y is equal to mx plus b form. They're not linear. And I will say lots of disciplines use nonlinear mathematics. Here I'm only going to talk about the sorts of skills that I think are important for students of economics. So for engineers, physicists, biologists, and others, if you guys have found your way here, what's important for you guys will probably be a little bit different. I will also say, once we come to think about calculus, this will give us many more tools that we can use to understand the behavior of all different types of functions. But even without calculus, there are things that we can do in order to understand these functions, and that's what I want to talk about in this video. And for students of economics, one really important skill is sketching such diagrams, even just roughly. One very simple approach that we might take is just to plot some points and link those points up to draw the function. So for my students, often I'll just take a very simple equation. Let's take y is equal to x squared as an example, and let's plot some points and sketch it together. So I'll make a table, and let's think about finding our value of y when x is, say, let's 0. So if x was 0, y would be equal to 0 squared, which is just 0. If x is 1, y would be 1 squared, which is 1. If x is negative 1, y would be negative 1 squared, which is 1. If x is 2, y would be equal to 2 squared, which is 4. If x was negative 2, y would be equal to negative 2 squared, which is 4. If x is equal to 3, y would be equal to 3 squared, which is 9. And if x is negative 3, y would be negative 3 squared, so 9. So I'm just considering some values of x. It's not completely random. I chose x is equal to 0 because that will tell me about the y-axis intercept, so what happens when our function hits our y-axis. And I'm also choosing positive and negative values here because I want to see what happens in those domains. For economics, context and/or theory might help you determine what values you choose. In any case, we can now plot the points on our axes here for this function. So when x is 0, y is equal to 0. When x is 1, y is equal to 1. And when x is negative 1, y is equal to 1. When x is 2, y is equal to 4. And when x is negative 2, y is equal to 4. When x is 3, y is equal to 9. And when x is negative 3, y is equal to 9. So we can join those points together and we can see that the function here will form a bowl-like shape that sits right on the origin. So that's our sketching of y is equal to x squared. And sometimes this can be really illustrative for students. You can also think about variations like y is equal to x squared plus 2, or we can raise x to a different power, maybe to the half. These sorts of exercises can really help you develop a familiarity with different nonlinear shapes. And once you do it enough, you won't have to worry much anymore. It'll just become more automatic. Now, apart from physically plotting points, you can also sometimes gauge the properties of a function just by looking at the equation. And this is a skill that is developed over time with repeated exposure to lots of mathematics. For instance, here, by considering y is equal to x squared, I can see straight away that my y values will always be positive, since x is squared and the square of anything is always positive. So I know that my diagram will always sit up here and never down where y is negative. Now, other things that we might do also is we can use known identities. We can find key points such as points of intersection either with our axes or with other functions. And we can also, as I just demonstrated, look at our equation, analyze our equation. So for another example, let's say that we're told that a firm's average costs and marginal cost functions are described by the equation. So average total cost is 121 over Q plus 3 plus Q. And marginal cost is 3 plus 2Q. And let's say that I wanted to understand how these curves behave, how they interact with one another, and how they look. Now, I can tell straight away that marginal cost is a linear function. In fact, if we have costs on the vertical axis and quantity on the horizontal axes, our curve here will be upward sloping with a constant slope of 2, and the cost axis intercept will be equal to 3. So this is just an application of the slope-intercept form of the equation of the line that I spoke about in one of the earlier videos. Average total cost, however, is definitely nonlinear. I can tell straight away because we have Q on the denominator. So that first term, 121 over Q, Q is on the denominator, and that points to nonlinearity. So I can do a few things here. The first thing I can check is what happens to average total cost when quantity is equal to 0. This will tell us about the cost axis intercept, so where average total cost hits the vertical axis. So substituting in Q is equal to 0, I find that average total cost is equal to 121 over 0 plus 3 plus 0, and here we cannot divide by 0. This is not defined. And this means that there will be no cost axis or vertical axis intercept here. This function is not defined at Q is equal to 0. In fact, what we can see though is that as quantity gets really small, this first term here, 121 over Q, will get really big. And this will form what we call an asymptote to the vertical axis. So average total cost will get really large as quantity approaches 0, but it will never actually cross that vertical axis. So I'll just put in a few values to show you what's happening to this function at small values of Q. So if Q was 0.25, 0.5, and 1. So if average total cost at Q is equal to 0.25, well, that will be 121 over 0.25 plus 3 plus 0.25. And that's 487.25 if you work it out. And note that 487.25, the value of that is driven mostly by the value of that first term. So 121 over 0.25 is equal to 484. All right, let's increase quantity a little bit. So let's say quantity is 0.5. So 121 over 0.5 plus 3 plus 0.5 is 245.5. Again, the bulk of that value is due to that first term. 121 over 0.5 is 242. All right, if quantity is equal to 1, we get 121 over 1 plus 3 plus 1 is 125. So at very small values of our quantity, average total cost is large because of that first term that's getting really big for small quantities. But as we increase our quantity, these effects become less prominent. Our average total cost is decreasing. We're going from 487.25 to 245.5 to 125. That's a decreasing behavior of our average total cost for small values of Q. Now, as Q increases more though, this last term, that Q value will start getting bigger and it will eventually get so big that average total cost will start increasing as Q increases. And at the same time, that first term, that 121 over Q will become less crucial because for large quantities, that fraction 121 over Q is quite small. So I'll show you, imagine evaluating average total cost if Q is 1,000 and then 2,000. So if Q is 1,000, average total cost is 121 over 1,000. That's a very small number, plus 3 plus 1,000. So that's 1,003.121. And the bulk of that value is being driven by that last term, that plus Q at the end. If Q was 2,000, average total cost is 121 over 2,000 plus 3 plus 2,000, which is 2,003 and some change. So you can see for larger values of Q, average total cost is increasing. As we increase Q, average total cost increases. And it's really the behavior of that last term plus Q at the end that's driving that, and the fact that that first term, 121 over Q, it's very small for large values of Q. So actually, in summary, I can see from our equation, just by looking at our equation, that our average total cost will initially decrease, but then when Q gets a bit larger, it will start to increase. So there is actually a bit that I can understand just by thinking about the equation. All right, well, the next thing we can do is look to our theory or to see if that says anything, or rather to some logic in this case that is very commonly used in economics, and that is the relationship between average and marginal things. So here we have average and marginal cost. And specifically, it must be the case that if the marginal, so the marginal is the next or the additional, is greater than the average, then the average will increase. If the marginal is less than the average, then the average will decrease. And this is pretty intuitive, but apologies if you've never seen this before. The intuition is that if we're thinking about costs, if our marginal cost, so the cost of the next additional unit, is higher than the average, then our average will be increasing. If the cost of producing the next or additional unit, that's the marginal cost, if that's less than the average, then by producing that unit, you will be dragging the average down. Your average will be decreasing. So this actually means that our marginal cost will intersect our average total cost like this. So for our quantities here, the marginal cost is less than the average total cost. So average total cost is decreasing. For the quantities here, marginal cost is above average total cost. So average total cost is increasing. Now where these two functions meet, where they intersect one another, average total cost will neither be increasing or decreasing, so that's right at the minimum. That's right at the point that the function turns. It goes from decreasing to increasing right at that point of intersection. So I've used some logic to understand more about how our curves here are behaving, and apologies if that's a bit much for you, you haven't heard of that logic before. I just want to demonstrate how much we can do without calculus, how we can still, in many situations, figure stuff out. All right, now what we can do is we consider mathematically where these curves intersect. So we can use the substitution techniques that I discussed in the previous video, where I considered solving a system of two linear equations. So basically I want to know where ATC is equal to MC. So I can substitute ATC, that's 121 over Q plus 3 plus Q, where that's equal to MC, which is 3 plus 2Q. I can take away 3 from both sides. I can take away Q from both sides, and I get 121 over Q is equal to, well, 2Q minus Q is Q. I can multiply both sides by Q, and I get 121 is equal to Q squared. I can take the square root of both sides here, and so Q will be equal to plus or minus 11, but we only take the positive value because we're only taking quantity to be positive in this application. All right, substituting Q is equal to 11 into either average total cost or marginal cost, we find that, I'll use average total cost first. ATC is equal to 121 over 11 plus 3 plus 11, which is 25. Now confirming this with our marginal cost, we find that MC is 3 plus 2 times 11, which is 25. So it will look like this on our diagram. And so you can see I used a couple of methods to draw out our average total cost curve in particular. I looked at the equation, I had to think about what was going on at different values of Q. I checked intersection points, I checked the axis intersection point, and also where marginal cost intersects average total cost. And I used this logic about the relationship between marginal and average to help me along as well. Now, lastly, you can also go onto a graphing calculator or website. I use Desmos. You can jump onto these sites really quickly to give you a visual if that helps. So I've plotted our two functions here. Over time, you will pick up patterns and it will become easier and you won't have to do stuff like that anymore. So I hope that this helps. When we go into calculus, that will give us more tools in order to understand these sorts of nonlinear equations. But as I hope that I've demonstrated here, there's also a lot we can do without that. As always, thank you so much for watching my content. If you would like written notes to help you on your journey, or even just to support this channel to help me make more videos, you can visit my store. The notes include lots of practice questions with solutions which can help you solidify your understanding of the skills discussed in these videos. If these videos have helped, please like and subscribe, comment, share, all of that. It all helps. Any feedback also is super welcome. Thank you so much for watching my stuff, everyone. Have a great day.